All right, guys. So thank you so much for checking in. As usual, I'll read through these a little bit later. And if you're still finishing your check-in, please, that's fine. I'm not going to remove this screen or anything. We're just going to be getting started here with our lesson on 9.2. All right, so I'm going to progress. Oops, that's not what I want to do. I want to do that. We're going to move to make the second screen available. All right, and this has our objectives for section 9.2, test about a population proportion. All right. After this section, we should be able to state and check the random 10% in large counts conditions for performing a significance test about a population proportion. These are the same 3 conditions that we had to check previously in chapter 8. We need to be able to perform a significance test about a population proportion, interpret the power of a test and describe what factors affect the power of a test, and describe the relationship among the probability of a type 1 error, significance level, probability of a type 2 error, and the power of a test. All right, so those are the things we're going to look at hopefully today. If not today, we'll get to them next time we meet, but we'll get through most of them. All right, so as in chapter 8, we introduced 3 conditions that should be met before we construct a confidence interval for an unknown population proportion. The random 10% when sampling without replacement and large counts. These same 3 conditions must be verified before carrying out a significance test. Right? So again, we have basically the same set of conditions, and now we're retitling it conditions for performing a significance test about a proportion. Random, the data come from a well-designed random sample or randomized experiment. 10% when sampling without replacement, check that n is less than or equal to 1/10 of n, where little n is the sample size, big N is the population size. And large counts, both n times p naught, and p naught is the assumed proportion from our hypothesis, h naught, the null hypothesis, and n times 1 minus p naught, or at least 10. So these are the same 3 conditions we've been working with, right? So we need to have these guys. We need to check them every time we want to do a significance test about a proportion. Okay. If you would like a moment to write anything down, please raise your hand. Excellent. All right. Oh, never mind. Oh, back up. Next. All right, so here's the first problem for you guys to solve. All right, and this is pretty straightforward. A recent report claimed that 13% of students typically walk to school. Deanna thinks that the proportion is higher than 0.13 at her large elementary school, so she surveys a random sample of 100 students to find out. Are the conditions for carrying out a significance test met? You'll have to select yes or no, and then explain how you know that they've been met. Alrighty. Okay. So we seem kind of split right here. We have 8 yeses and 5 nos as of right now. Would someone who thinks, well, for yes or no, someone want to tell me why they made their selection? I see some of you guys have written your explanations, but I'd like someone, if they're willing, to speak or type in the chat as to why you chose yes or no.
I just think that elementary kids are not like the perfect subject to like do a survey because it's very unpredictable on what they will put because they could just be playing around with the survey, I guess, or just put something random.
Okay, fair. Right, that's true. I mean, looking at who we're sampling here, they're not the most reliable people, right? That's fair, right? But is that something we're supposed to check for in our conditions? Right. We have to consider the scenario we're given and say, okay, we have these three things we're supposed to check for, right? We could address that later on in our study saying, hey, these are some possible sources of error, right? Some sampling error that could make our results unreliable or could explain why we got results we didn't expect. Yeah, but thank you, Antonio. It was a really is a very good observation, right? And it's actually definitely something we want to consider when conducting an experiment and taking samples. Who are the people we're collecting samples from? Are they reliable? Unfortunately, in this instance, it's not something, we're not at that place in the experiment, so to say. So for this scenario, we do have a yes, these conditions are met. Okay, and I'll slide my OneNote stuff here. Zoom in a little bit. So again, with this example, walking to school, random, the sample was a random sample. We did that, that was done properly. 10%, the sample size of 100 is less than 10% of the school's population. We're assuming that because they didn't tell us the size of the school, they just said it's large. So we're just making an assumption based on the context given. Large counts, we have 0.13 times 100. The sample size is 13, which is greater than or equal to 10. And 0.87, right? 1 minus p times 100 is 87, which is also greater than or equal to 10. So the large counts condition has been met. So based on just those three conditions, which are like actual things we can check for, like they're hard things. They're not like the sampling error type of things that Antonio brought up, that he validly brought up, right? Those are good things to consider. But unfortunately, it's not part of our conditions to proceed with our significance test. All right. Is there anything I can clarify about this one? All right. So we're gonna make the next one available here. All right, so then what is a significance test, right? We've previewed what this is in section 9.1, right? So a significance test uses sample data to measure the strength of evidence against H0, right, our null hypothesis. There's some principles that apply to most tests, right? First, the test compares a statistic calculated from sample data with the value of the parameter stated by the null hypothesis. Values of the statistic far from the null parameter value in the direction specified by the alternative hypothesis give evidence against the null hypothesis. So that means essentially values that are a lot of standard deviations away from the assumed value or assumed parameter value with the null hypothesis give evidence that that null hypothesis might not be true. Okay, think of it, if we think of it as that bell curve, the null hypothesis is the mean right in the middle. If we get a test statistic that's way out on the tails on one side or the other, depending on the direction of the alternative, that gives us evidence that, well, this assumption might not be correct. Right, and then we have test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis H naught were true. In standardized units, that is, the test statistic equals statistic minus parameter divided by standard deviation of statistic. It's essentially a z-score. Right? This is very similar to the way we calculate a z-score with a normal distribution. Right? It's just we need to use our different things that apply to sample data and sample proportions. Right? We'll get more specifics on that on the next slide. Does anyone need a moment to write anything down from this slide? Please raise your hand. Okay. So then the next thing is the Z statistic. Very similar again to the Z score that we've used with normal distributions, right? Our standardized score. When carrying out a significance test about a population, we use the test statistic of a Z statistic. We call it a Z statistic because it is similar to a Z score, and will be used along with table A to help find the p-value for our significance test. Right, the Z statistic is Z equals p hat minus p divided by the square root of p naught times 1 minus p naught divided by n. Right, it's very similar to the Z value that we used in chapter 8. I forgot to mathify these things. Sorry, guys. All right, where p hat is the sample proportion, p is the parameter value, and p naught is the null hypothesis parameter value. Typically, p and p naught are the same value. All right, so in this formula, we have p hat minus p, and then we have p naught times 1 minus p naught underneath the division symbol and the square root sign. Those are typically all just going to be the same value from our null hypothesis. All right, and I'm actually going to move to the next screen because we have this same exact formula on the next screen, more formalized with its like definition and such and things from the textbook. So we're going to open this guy up. So we have the one sample Z test for a proportion. This is the inference method. All right, for our significance test. It's the one sample Z test for proportion. All right, similarly to chapter 8, we had the one sample, what they call it, Z statistic, I think, or Z something, Z score. I forget exactly what it's called, I'll look it up later, but one sample Z test for proportion is the inference method. So when you get to the plan step of your 4-step process when solving one of these problems. This is the method you will use. You'll say you're going to be using if conditions are met. All right. So choose an SRS of size n from a large population that contains an unknown proportion p of successes to test the hypothesis h naught or p equals p naught, right? Where so this p sub 0, right, is the assumed proportion, right? We compute the z statistic with z equals p hat, where that's the sample proportion from our sample data, minus p divided by the square root of p sub 0 times 1 minus p sub 0 divided by n. Big thing to remember, these two values, p sub 0, 1 minus p sub 0, when you add those two things together, you should get 1. Right, so if the assumed proportion is 0.25, 1 minus 0.25 is 0.75, 0.75 plus 0.25, 1. Right, if the two numbers you use here that you multiply together in that square root sign are not adding up to 1, you did something wrong. You've got an error somewhere. All right, find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis h sub a. And we have our little set of graphs here, right? So if our alternative is that the true value is greater than the null hypothesis, then we're looking at our standard normal curve and the z value, the proportion of the curve greater than that z value. First, assuming less than, the alternative is less than, then we do the proportion under the curve less than that z value. If it is not equal to, we have a two-sided alternative. Then we take the proportion that's less than the negative z and greater than the positive z. And essentially what we end up doing is doubling the p-value that we find using table A. And we have a two-sided alternative. Is there anything I can clarify about this part? Or is there any questions so far? Can you raise your hand if you need time to write anything down? All right, so then this one is actually a problem that you can do that we're going to go through here. So this refers back to screen 4, the first walking to school problem we checked the conditions for already. We want to calculate the test statistic. All right, based on the fact that Deanna's survey, 17 students in the sample said they typically walk to school. So now we have a sample proportion, right? We'll have to do 17 divided by 100. We have a sample proportion. I'm going to calculate the test statistic and find the p-value using table A. I have a link to the formula sheet and tables right here. That should link actually into Canvas to where that page will pop up with the formula sheet, and table A is on there. You are welcome to type in your responses in the entry box here, or you can use the upload image button and just do your work by hand and then take a picture of it and throw it up in here. All right. So again, you're going to need to use this z-score calculation, the z-statistic calculation. Use that z-score the same way we have using table A previously, find the proportion. Right? But you do need to consider what is your alternative hypothesis based on our original context in screen 4. All right, guys, we're going to take a look at this. I know that it probably hasn't been enough time, and that's okay. If you didn't have a chance to complete your work on this one, that's totally fine. We'll get there. 8 minutes for the first time of trying to do this probably isn't enough time, but because of like the time constraints we're on, we're going to look at how to do this. So I'm going to pull that up. please feel free to continue do this or whatever you need in your notes to make sense of this. So right here. All right, so we'll start with part A here. All right, so first we have our Z formula. This is just a habit of mine. Anytime I use a formula, I write it down in its general form first, and then I plug in all my values afterwards. I also recorded, in which I saw what some of you guys did, what my hypotheses were, right? Which we have here. These are our hypotheses, right? And we have that little like verses to say like we're testing these two things against each other. The null hypothesis is that the proportion is 0.13. The alternative is that it's greater than 0.13. That's what Deanna thinks, is that there's actually more people walking to school than 13%. Our test, another test, our sample proportion, right, is that p hat, 17 over 100, 0.17. All right, p is equal to p, the null proportion, right, from our hypothesis, 0.13. Right, this I've written because of how the formula for the test statistic is written, right? And so I'm going to plug in all my values, right? We have 0.17 minus 0.13 divided by the square root of 0.13 times 0.87 divided by 100. It's important that if you're putting this in your calculator, like your graphing calculator, the square root, this entire fraction is in the square root. Right? It's not just taking the square root of the top part of the fraction or just the bottom part, it's the entire fraction. So you have to be mindful of that when you type it in your calculator. Right? We ultimately get the test statistic of 1.19. All right, so we're done with part A. Part B, right, which we'll just zoom out just a touch here. All right, part B, right, is now finding the p-value, right? And so we just take, all right, our alternative was that we're greater than 0.13. And so we then just apply that to our Z statistic here. Say, well, what's the probability of Z being greater than 1.19? Well, again, table A doesn't give us greater than proportions, it only gives us less than proportions. So we convert that using, I always forget what this thing is called. We say if it's the probability of Z being greater than 1.19 is equal to 1 minus probability of Z being less than 1.19. So we use this conversion, we get 1 minus 0.8830. And again, that's from finding 1.1 along the left-hand column, right? And then 0.09, right? Which when we put those together, we get 1.19. Right? And those intersect at 0.8830 on table A. So we subtract that, we get 0.117. That is our p-value. Right? In the normal curve, right, this is kind of what it would look like. We have the values of Z, which look very similar to just the standard normal curve. That's what we're using, right? 1.19 is going to be right about there along our horizontal axis. The proportion greater than 1.19 is 0.117, and that is the p-value. At this point, we have not been asked to make a conclusion. We've not been asked to compare that to a alpha, like a significance level. So we're done. We've completed what the problem has asked us to do. We found the test statistic, we use that test statistic to find the p-value. We're done. Is there anything I can clarify? Is there any questions? Sorry about that. Elena, if you'd like me to look at your work, you're more than welcome to put the photo into the chat in Teams. If you have the Teams app on your phone, just like in a text message in like Messenger or something like that, you can add a photo that you've taken on your phone into the chat using the Teams app on your phone. If you'd like me to take a look at your work, you're welcome to do that. All right, so moving on. We at 9:24. Okay, good. All right, so that was our first kind of example, right, dealing with our proportions. The next thing we're going to consider, I'm losing people, is our two-sided tests. Right? The one that we just did was a one-sided test. We were just considering, okay, being greater than the null hypothesis. The p-value in a one-sided test is the area in one tail of a standard normal distribution, the tail specified by the alternative. And this is what we just saw. In a two-sided test, the alternative hypothesis has the form h sub a, p not equal to p sub 0. Right, so it's just not the same as the null hypothesis. It could be bigger, it could be smaller. We're just saying it's not the same. The p-value in such a test is the probability of getting a sample proportion as far as or farther from p sub 0 in either direction than the observed value of p hat. As a result, you have to find the area in both tails of a standard normal distribution to get the p-value. Right, and that's what we saw in the graphic over here. At the bottom of our little definition square, we have the different normal curves with the proportions you would be finding, the tail proportions, based on the alternative hypothesis. All right. Now, there is a strong connection between two-sided tests and confidence intervals. Right. The 95% confidence interval gives an approximate range of p sub zeros that would not be rejected by a two-sided test at the alpha equaling 0.05 significance level. A two-sided test at significance level alpha equals 0.05 and a 100 minus 1 minus alpha, 100 times 1 minus alpha percent confidence interval, 95% confidence interval, if alpha equals 0.05, gives similar information about the population parameter, right? Meaning that if my significance level is 0.05, that means I could calculate a confidence interval of 95% to find the plausible values of the proportion. Essentially anything that falls outside of that interval would lead to me rejecting the null hypothesis because those values are outside of what it should be if the null hypothesis were true. So it's a different way of viewing the significance level, right? We have our, if the p-value is greater than alpha, right? Yeah, if the p-value is greater than alpha, then we fail to reject. And if the p-value is less than alpha, then we reject. Okay, and so this gives us another way of testing this when we have a two-sided test. Don't get hung up too much on this. It's just a connection between the things that we've seen so far. Is there any questions? Anything I can clarify? So then, now that we've seen kind of like all the parts that we're going to be using, this leads us to, again, our 4-step process for performing a significance test, very similar to the 4-step process of finding a confidence interval. All right, to perform a significance test, we state hypotheses, check conditions, calculate a test statistic and p-value, and draw a conclusion on in the context of the problem. 4-step process is ideal for organizing our work. Right? In the state part, what hypotheses do you want to test, and at what significance level? Define any parameters you use. If you're using p, what is that the proportion of? What are we trying to test for? What's the parameter? Right? Significance level. If you're not told a significance level, default to 0.05. That's kind of like a standard. They range from 0.1, 0.05 to 0.01 for alpha values. If you're not told which one to use, just use 0.05. Okay, this is a default. Choose the appropriate inference method. In this case, we only have the one for significance levels, and that is the one sample Z test. All right. And then check conditions. Same 3 conditions. Do, if the conditions are met, perform calculations, find the test statistic, find the p-value. And then finally conclude, make a decision about the hypothesis in the context of the problem. Right? In the conclusion, you should say whether or not you reject or fail to reject the null hypothesis, and whether you have or do not have evidence to support the alternative. That's kind of the main stuff you need to include in your conclusion. Okay. And I think this is a good place to stop for today. Well, wait, we'll do no, that's going to take a while. We'll do that next time. The next problem is a full 4-step process that would take a while. So we'll get into that one next time. All right. Is there any questions? Anything I can clarify? Okay. So then, while I'm sharing my screen here, we'll look at just a little bit in the course here. In the calendar, right? Obviously, we're in March. We're on the 23rd, 24th. Spring break starts on the 25th. Hooray! I will link the PowerPoint presentation stuff that's from like the textbook slides that I use sometimes, along with this Desmos activity in our calendar here. You'll also be able to find it. Well, the Desmos activity will be in here with the section 9.2 stuff in the module, which also has the study guides for section 9.2 and 9.3 and practice problems and solutions for 9.2 and 9.3. Those are all updated. I have not made the assessments yet because we're just not there yet. We're not ready for them. But I will get there. I'll probably have them made over spring break. So I do encourage you to check out like the notes and resources and the practice problems. There's lots of AP Daily videos for section 9.2 and 9.3 that are very helpful, as well as like worked example problems from the textbook. So I highly encourage taking a look at some of those things if you have time, and doing the other practice problems. Otherwise, we'll get all this stuff loaded along with the recording. Should be ready later today. If you have any other questions, comments, concerns, please let me know. Send me a message, something, and I will see you guys in like, shoot, I don't know. How many weeks is this? 2 weeks. 2 weeks. I'll see you guys in 2 weeks. Have an awesome rest of your week, an awesome weekend, an excellent spring break, and we'll see you all later.